Welcome to the 5th unit of the module on control design. So, as discussed in the last unit that from today we will be discussing on the special type of instructions, what are the control signals involved in, and we will be mainly talking about control instructions which are of jump, handling of function calls, etc., which we call as transfer instruction. So, this unit basically will be covering on control signals, micro instructions involving transfer instructions like jump, call, etc. So, we will be talking after looking at the different type of control signals for general type of instructions. In today's unit, we are going to handle jump, call, etc., which come under the category of control transfer instructions. So, basically in the units, what is in the unit summary? We will first discuss about the unit summary before going into the depth of the unit. Basically, as we already know, the control transfer instructions are of two types, conditional and unconditional. Unconditional and conditional as the flow in the thesis in the slide. So, what is the unconditional jump instruction? An unconditional jump instruction is very simple, like jump, go to that memory location where the corresponding instruction is there. Maybe you call a function. So, that is an unconditional jump. And what is a conditional jump? When you look at these flags and decide what to do, like jump on 0 to some memory location 30 where the next instruction is there. It will jump only if the 0 flag is set. So, that way we can differentiate the control transfer instruction as conditional and unconditional. Basically, now what are the basic steps involved, or the basic control instructions or micro instructions involved, or the control signals involved in each of the steps. As we have already discussed in the last few units, that basically the 3 steps, that is the first 3 steps basically involve fetching of the instruction. So, in this case what happens? In the step 1 basically we load the program into the bus, PC into the bus, and we give it to the memory address register, so that the corresponding instruction can be fetched. We make the main memory in read mode and we get the value of the program or the instruction in the memory data register in the 3rd stage basically. So, basically that is what is the thing, and then we say that, but here there is slightly difference in case of a jump instruction or transfer instructions. In general type of instructions, we take the value of the program counter to the bus, put it in the address register, and then wait for the corresponding instruction to be obtained in the memory data register. And also what we do, we also try to increment the value of PC to the next value to point to the next instruction. But in this case, we do a slightly separate stuff over here, that what we do, we actually also start the incrementing of the PC here, but also we store, as we will see the requirement, what is the necessity, we also put the temporary value of PC into a temporary register Y. We will see that why it is required later, because in the time at the same stage when you are trying to increment the PC, as well as you will have to store the value of the PC to a temporary register. We will see that storing of the PC in a temporary register is something different which you are doing in transfer instruction, and we will see later see what is the importance of that. Okay. Other things like set the marks so that the constant is added, that is actually pointing to the next instruction, that remains the same. Okay. Then basically what else, load the output of the ALU to a temporary register, that is PC equal to PC plus 1, all these things will be similar, but only one extra thing is basically the control signals in the first step load the value of the PC into the memory address register, increments the value of PC, that remains the same, store it in a temporary register Y is a special extra thing which we do for the control instructions. All other part remains same, so I am not elaborating. The second stage is very similar. Basically bus value will go to PC, that is PC equal to PC plus constant, that is the next transfer, output the contents of the temporary register to bus. These are very simple. Halt the value of the PC or halt the value till the memory says it is okay. Once it is done, you can go ahead. This is very similar to the second stage. The 3rd stage is also very similar. The 3rd stage basically says that the memory read is okay. So, basically the output of the memory data register is going to the instruction register, as simple as the fetch. So, up to this is more or less similar, that is you fetch the instruction and in the instruction register. Only one extra thing we do here, you just keep it in mind, that we will store the value of program counter in a temporary register Y. Now, from 4th step onwards things start changing basically. Now, in this case, in previous case we have seen how to add, how to store from memory to the registers, but here actually it is something going to a jump space. For example, let us take the instruction called jump unconditional to say 30, that we want to jump to that memory location. That is what is the execution part here. So, in this case what you have to do, you have to somehow load the value of program counter in the next stage to 30, that is what is the execution to be done. Because when you want to execute some instruction which is in memory location 3030, what you have to do is to simply load the value of PC to 3030 and your job will be done. So, the execution part will take care of that. So, what we do? Input the value of offset to CPU bus, which is the second operand of the ALU. Now, we will see what do you mean by an offset. The offset basically is a part of the instruction register which actually goes to the CPU bus basically. So, what is an offset? Offset is present value of PC minus M, and you take generally the positive value out of it. So, if you assume that the present value of the PC is equal to 10, for the time being let us assume that is equal to 10. So, your offset will be 30, this 10 minus 30, this is the positive you are going to take it. So, it will be 30, 20. So, this is what is actually your value of the offset will be. So, that is what will be given by the instruction register. So, instruction register will generate the value of PC. Okay. Next, what you do, the offset is set, the offset value is this one, and it is saying the input value of the CPU bus is the offset, which is the second operand to the ALU. That means what? We are going to generate the jump address and we are going to load it into the PC. That is what is the job of the fourth step. So, what fourth step does? Fourth step actually generate this offset. Offset is nothing but the present value of CPU or present value of the program counter minus the M, which is your memory location to be jumped. That value is called the offset. The positive, you always take the positive value from it. So, in fact, so 3020 is the value of the offset in this example. Now, what you do? So, basically, so if you are considering single bus architecture, the 3020 value will be a operand. Next, what you do? The input to the multiplexer is 1. So, input to the multiplexer is 1. If you remember the previous lecture, that is now not going to take any constant, it is going to take the value from the temporary variable y. So, what is the temporary variable storing here? We already discussed temporary variable y is storing the value of PC. As I told you, this is only extra thing that is happening in the first 3 instructions when it is a jump instruction. In all other cases, there is no involvement of any y over here and the PC is directly updated. So, now y is another input to the ALU, it is the PC, and this is your offset, which is nothing but present value of PC minus M. Then actually you configure the ALU to do addition operation. So, finally what you are doing the content of PC, which is in Y plus an offset. So, basically what you are doing present value of PC minus M plus the value of PC. So, you are doing present value of PC minus M, that value already is the offset, plus PC. In fact, you are going to take the mod of it. So, basically what you are going, they will cut out and you are going to get the value of M. So, which is in this case is 3030 and which is actually loaded to a temporary register, that is your Z. So, in fact, it is slightly a roundabout way, means we do not directly take the value of 3030 and dump it into the CPU or dump it into the PC. Basically, we take an offset value and then we add the value of PC to it. These are actually this helps for relocating programs, because if I say that if I write the value of 3030 and say you are getting loaded at memory location some memory location called 700, so there is always an offset and there is a relative addressing. To take care of the relative addressing, so all this roundabout way of generating the address is present. I cannot go into depth at this point on this part here, because it is a part of something called assembly language programming. So, in that, because to maintain the relativity and relative addressing, we go about a roundabout way rather than not directly taking the value of 3030 and loading it into the program counter. We just take a offset value first and then we again add the value of offset value to present value of program counter. So, they get cancelled out and you get the value of 3030. So, it actually helps in relocating programs and some kind of other relative addressing mode, which you want to read in details, you can find out from the any book on system programming. So, next is very simple, as I told you. Now, the Z, that is the output of the ALU is stored in Z, which is nothing but the present value of PC plus offset, which is nothing but equal to M. So, offset, that is already told, that is nothing but value of PC minus M, this is the case and you get the M. And basically this one you will now update, Z will update to program counter. So, you are now jumping to that instruction and you are actually executing it. So, this is basically in summary what happens for the control signals and the micro instructions that takes place in a jump kind of an instruction. Anyway, so that was a very brief summary that what happens and what are the control instructions, what are the flow that takes place for a jump instruction. or any kind of control transfer. So, what are the objectives of this unit? First objective is a comprehension objective which tells explain the issue related to design of control transfer instructions, like what are the special arrangement has to be made, if the PC has to be backed up, what else extra instruction you require, like here for example the PC is also backed up at a temporary register Y, and not only PC equal to the increment is stored into the PC, but along with that the updated value of PC is also stored in Y. It is something extra. Then design use of flags while designing a control transfer instruction like branch on 0, branch on positive, branch on negative, etc. How the flag registers are used. That explanation, that synthesis you will be able to do. And finally, the design objective, design the instructions for call and return. That is, you will be able to design instructions which are involving function call and return. Now, before we start the module unit, let us basically look at the single bus architecture, which is very similar. You have the program counter, then you have the memory address register, memory data register, very similar. Then you have the ALU, and there is a temporary register which called X, which is an input to this. There is slight difference. I mean, this is in the previous thing you might have seen this as Y. This we were calling at Y in the previous lecture, and this we were calling it Z. So, just is a way of nomenclature change. Let us keep it same for the ease of understanding or continuity. That is Y is the temporary register, Z is the output of the ALU. This is marks, these are constant 4. 4 actually is just an example. It can be the size of the instruction. Then the ALU basically, this is the ALU which does all addition subtraction. Then you have the temporary register. This is the temporary register, this is your register set from 0 to n, instruction register, control logic. One very important thing you have to note here is the flag register, which is there, but actually I am again drawing it here specially because it takes a very important role in any kind of a control instruction. So, because 0, carry, jump on, overflow, etc., all depends on the flag value set. So, this flag register is playing a very important role in basically determining the control signal. So, that is why these are special emphasis we have put on this one, the flag register. So, this is mainly shown over here. Okay, so, now with this let us start taking some examples of instructions and exactly see what happens. So, the first instruction will be dealing in very details by looking at the bus diagram, bus architecture, how the signals are moving, and other instructions we can have a very quick overview. So, jump 30, unconditional jump, that means the program counter should go to the value of 3200. So, if you look at the memory this way, so maybe this is 3200 is the memory location, some instruction may be there like say add or something. So, that will be loaded to the PC and PC will do it. So, somehow you have to load the value of PC to this value. So, maybe there is an instruction or it can be having a halt instruction or whatever. The idea is that I want to jump to this place and I want to get this value out of this instruction, or I want to execute this instruction. So, PC actually will have the value here, so it will make a jump instruction. So, somehow I have to load the value of program counter to 3200 and your job is done. Then actually program counter will execute from memory location 3200. Now, we will see how it happens basically. The first stage is already discussed, program counter out, memory address in, because why already we have discussed so much. So, let us think that this is memory location 10. From where it is executing. So, basically program counter is equal to 10, maybe the instruction called say jump 3200 is available at this place. So, what you have to do, you have to load the value of memory location 10 has the instruction jump 3200. So, already so many times I have discussed that this 10 value has to be loaded into the memory address register. So, basically program counter will be output, it will be loaded into the memory address register. You have to make the memory in a read mode because you want to read the instruction. Select will be equal to 0 because your select means that is the ALU mark select. So, it will be adding a constant add and Z in, basically the value will be written. So, if you will quickly look at it, look at the structure, what we are saying that value of program counter, that is 10, will be fed to the memory address register, and memory data register after a certain amount of time will get the instruction which is in that program counter memory address in the memory, it will be going to the instruction register. That is what is a standard thing that happens. Then and correspondingly PC out, memory address register in. After the second stage it will be MDR out, it will go to instruction register. But before that also this will actually happen after certain amount of time, because you have to give some time for the memory to respond. So it will actually happen in the third cycle. But in between we prepare to increment the PC. So we make it the value of 0 so that the constant can be added. So in fact program counter value is in fact the PC value is over here in the bus. Because PC out is there, it is going to the memory address register as well, it is available in the bus, and this is equal to 0. So constant 1 or 4, that depends on the instruction size, is there, and we are making Z in. That means here you have PC plus constant, that is 4 or whatever. That value is ready, and whenever we say Z out means it is ready. So in the second stage actually we will dump it over the PC. That is going to happen. So that is what program counter value will go to the memory address register, read it, select 0 means keep the value constant to be added, add is the mode, and Z in means output of the ALU will be stored in Z. Next what you do, PC in, that means already the arithmetic logic unit has dumped the value of PC plus constant in Z. So you are making Z out and you are going into the PC in, that is PC has been incremented, and we are waiting till the memory is ready so that the instruction is dumped into the memory buffer register in the third stage. Extra thing, again I am repeating, an extra thing, that is Y in is very special in jump instruction. This was not there in the any kind of add, load or store instruction. Now we will see what is speciality about Y in, that is Z out and Y in together. That means we are having Z out is having nothing, but it is having PC equal to PC plus constant, that is the next value of the program counter. We always store it in PC, that is standard, but again also we are storing in W in. What is that extra and how it will help? So if you look at it, program is constant, basically it is going to PC. We always store it because now PC is going to point to the next instruction. But for the time being also we are dumping it to Y. So that is actually called Y in. That is special. That PC equal to PC plus constant is dumped as well as to the PC as well as to the temporary register. We will see why it will be required. I can just give you an idea, a very basic idea of why, because the present value of PC may be say 10 will be stored over here, and after that the offset will be given to the second block. So in that case what happened, this is the present value of PC plus offset will again give you the value offset which will come later. The offset will be coming from the instruction register, it will be added to the value of PC and you are going to get the value jump address. Already we have seen how to calculate the jump address by adding the present value of PC plus offset. Because we have to add the value of PC not with a constant, but this time with an offset, so we have to have the value of PC stored in a temporary register. For all other cases, if you remember, the value for the first case, that is you have to increment PC, what you can do, you can load the value of PC in the bus and you can take the constant over here. So one operand is constant and another operand is the PC. But in this case, one operand is coming from the instruction register, that is the offset, and another one is actually your PC. So how can I have two things going to the ALU together? You could have done it is that you could have taken the value of offset and dumped it in Y, and you could have taken the value of program counter in the bus. That is also possible, that you take that you store the instruction register offset in Y and then you just float the value of PC in the bus and you can do it, add it. Another way is that you store the value of program counter PC in Y and float the value of offset and do it. That is actually a simpler way of doing it, because in this second stage you are anyway dumping the value of PC in the update value of PC in the program counter register. Same time, hand in hand you just take the value in Y and store it. After that you just take the value of IR in the bus and add it. That is a simpler way of doing it, rather than storing the PC first in the program counter only, that is the updated value of PC in this one, you are storing it. Then after some amount of time you do not go for this, you remove this, you do not update the value of Y with this, you take in fact the offset and you load it over here and then again take the PC, the roundabout way. So what we do, we take a simplistic approach. So what is the simplistic approach? The simplistic approach is first load the value of program counter in the memory address register, that is what we do, and make this is 0 so that the constant comes over here and the PC is already over here. So this is equal to PC plus constant and this was our Z basically. So Z in, so the Z will actually have the value of updated program counter. Then if you in the second stage you make Z out, so it will go into the PC, that is the updated value. Hand in hand also you dump the value of Y in the temporary register Y, you dump the value of program counter, updated program counter, and next stage you take the value of IR in the bus and that is the offset from the IR and add it. So up to second stage it is second stage is simple. Updated program counter value goes to PC. In addition, we are also storing the value of updated program counter in Y. Now let us see what happens. Then in the third stage is as simple as all other instruction, that is your memory is ready. So you dump the value of memory data register to the instruction register. That is the instruction, in this case jump 3200 is loaded into the instruction register. That is same as all instruction, that is loading the value of the instruction from the memory to the instruction register. This is a new field, new type of stuff which we are saying offset value of IR, because now you have to have the PC loaded with 3200, and already seen how we can get it. We can say that offset plus PC will actually give the value of 3200, because already we know offset is nothing but present value of PC minus 3200. So if you add the mod of it, so if you add the value of PC to it, you are going to get the value of 3000 to it. That is actually elaborated in this write up. You can read it from this slide. I can just clean it, but again I am telling you, instead of directly loading 3200 to the PC, we are taking a indirect way of doing it, like by calculating the offset value and adding. So this is actually going to help in many kind of relocatable programs or relative addressing mode, which you can read mainly in the any system programming kind of book, which can tell you what do you mean by relative addressing, etc. So for the time being, just you have to take in a black box that I am generating the value of 3000 in a roundabout manner, that is calculating the value of offset and then adding the value of PC. So what I am doing, I am saying that the offset value of IR equal to out, that means the instruction register will dump the value of this one. So instruction register has an inbuilt way of generating the offset, so it is out, select equal to 1, add and Z in. Select equal to 1, in this case if you observe, then you are not going to add, again I am going to look at it. So select will be now equal to 1, so that means you are going to take the value from this Y register, that is now, but this is nothing but your recent value of PC. And also at that same time you are also dumping in this location, let me erase the first part of the instruction, this one we are all erasing, okay, this is also erased. Now this PC is going over here, that is PC equal to constant, that is outdated value of next value of PC, and this is coming over here, and from the instruction register basically through this you are actually dumping the value of basically I should write it this way, you are dumping the value of offset. It is not the whole PC register, and we have already told that we sometimes take a part of the IR register. So in this case the IR register is slightly multifunctional, so it just calculates the offset and dumps the value over here. So here you are getting the offset, so if you offset you are adding with the program counter, so basically you are going to get the value of M, that is your jump instruction. So that is your M. So M will be fed to Z and it will be kept as input. Next stage you will just dump the value of Z to program counter and your job will be equal to done. So that is what is done. So in this case we are keeping the value of offset as out, select 1, that means you are going to take the program counter input to the ALU plus offset, and the value of Z in will be there, which is actually equal to M. Next is very simple, Z out equal to PC in. So whatever will be the value of Z out, that is nothing but M, that is the jump instruction, jump location PC, and your job is done. So basically this tells that 5 micro instructions are required to basically to complete this whole unconditional jump instruction, and these are the control signals generated, and how they are actually play a role in the single bus architecture we have discussed it in details. In the next few similar type of instructions we will not go in as details as I have told you, but we will just give a direction which will be more or less similar type of flow in the bus architecture, single bus architecture. Let's slightly changing the instruction mode, that is jump on 0, that is conditional jump you do over here. So first instruction will be same, program counter out, memory address register in, read, select, add 0. Then what you do, that is the program counter output, you will load it to the address register, so that you can get the value of the instruction in the third part, third instruction. From because in the third instruction or the third micro instruction, basically the memory will say that I am ready. So the instruction which will be loaded into the memory data register will come to the instruction register, as simple as that. And this already discussed, these are same for all instructions. Select 0, add and Z in means you are preparing to add a constant to the program counter. So it is done. So Z out in this case is nothing but program counter plus updated constant, which will actually upload in program counter, as well as we are a special case of jump instructions, we are storing it in Y in. That job is done. Next by WFMC means your memory is now ready. In the third stage what happens, basically the memory data register will dump the value, that is the instruction, to the instruction register. That job is done. Next will be very similar, that you have to take the offset from the instruction register, add it, and in this case is important, then you have to add it, select is equal to 1, just word it. So, this will be the output, select equal to 1, that means you are going to take the temporary value, that is y, and not the constant, and you are adding it, that means offset plus PC, that is actually going to give you the m where you have to jump, and then you are actually save the value in z. Already this is very similar to the last unconditional jump instruction. Here is a very important thing that is coming up, is called if not flag 0, then n. I am not going into the internal details of this micro instruction corresponding to this. This is very simple. What happens basically, this, if you look at it, this flag register, this is your flag register, it is a register with some special multifunction. So, whenever you are saying that the opcode says that basically it is a jump on 0, so just you look at the flag which corresponds, the flag bit which corresponds to basically your 0 flag. So, if the 0 flag is not 0, basically what it does, it says that if 0 flag is not 0, then n. That very simple, it will just take the value of the PC to a reset value or to the last value of the program counter at that micro instruction. So, it says that in the 5th control step, we will update the PC only if the condition is satisfied. If it is not 0, then n is checked by the instruction decoder block, and then it actually skips the next step, or actually it ends the microprogram. Skipping is not a proper word in that sense basically. So, what happens, that is the instruction register in this case will just check the 0 flag. Actually, in fact, this is a input to the 0 flag. In fact, this one is actually input to the instruction decoder, or in fact we can have a connection over here. I am not going into inner details because it will actually make it more complicated, but the idea is very simple. So, what happens? The output of this one is basically the instruction decoder reads the flag bit, and if the flag bit, 0th flag bit is not set, is not 0 basically, then what you do? You just reset the value of PC to the last address of the microprogram, that is you are ending the microprogram. That is, you reset the value, or in this case as you will see, you just return to the program which, to the instruction which is calling the micro instruction. That means you are ending the sequence of micro instruction here itself. That means you are actually trying to go to execute the next macro instruction. So, just a reset of the PC, that is very simple. But if it is satisfied, then what is going to happen is as simple as take the value of z in and put it to the PC. That means at this point of time, when you are saying offset plus select 1 and add, when you are doing an z in, that is these 3 parts basically, these 3 parts, that is offset value of IR, select and add. In this case you are adding y, temporary register with the value, that is actually having the value of PC, that is again let me just quickly look at it. So, this one you are adding it, this is the offset, this is the PC, this part you are adding, this is the part you are adding and keeping it in Z. But whether you will upload the value of Z to program counter will depend on whether what is the value of this flag register. So, if the value of the 0th flag in the flag register is satisfied, that will be checked by the instruction decoder, then it will not do anything. It will just go to the 5th stage. 5th stage will just set Z out and PC in. But if it is not set, the 0th flag is not set, what it will do? It will just instruct the instruction decoder to reset the value of PC, or actually return, in fact return to the macro instruction which actually call the sequence of micro instructions. Now, we will shortly see what is call and return. That means, just for the time being, assume that it just somehow resets it so that nothing more gets executed and basically your micro program ends. So, either there is 2 options. In this case, either you end it, that is you return to the macro instruction and go to the next instruction, or you go to PC in. That means, it says that jump on 0, jump on 0, let me see the instruction. So, it is a jump on 0, JMP 0. So, JMP 0 is the instruction of code on and you are going to say some location 3200. So, till this point I am ready with this value in Zin. Zin has the value of 3000. Just I need to either update the program counter with 3200, that is simple like Z out PC in, or I have to reset, that is in the memory, some memory location we are assuming a 10 memory location have the instruction JMP 0 3200. So, this one actually called the sequence of micro instructions which we are discussing, these 5 micro instructions. If in the 4th stage you find that this 0th flag is not satisfied, then I am not going to execute this 5th micro instruction. I will reset my PC in such a fashion that actually I will go to the 11th instruction and you start from there itself. Else you will reload it and the other set of equations will execute. So, this actually explains how slightly if there is a conditional stuff, then how slightly it changes. I am not discussing in details about how to check if zero flag is not equal to 0. It is very simple, just it is a kind of a AND gate or an XOR gate based check, and just you have to reset the value of PC or return to the next macro instruction. Returning will be dealing it later, but if it is 0, then just you do not have to do anything, you do not reset, you just go to the next macro instruction. It is very simple implementation. Before going to jump and return, we have another simple instruction I am taking, which is a sign flag. It is saying that branch to 3200 if the sign flag is 1. That means it is a sign bit has been set. Same steps, no difference. So, in this case fetching the instructions, and then in this case instead of your 0 flag you are going to check the sign flag. If the sign flag is set, then it is fine, and if it is not set, you will actually go to the end, that is you are going to reset it. But again I am just using this one to see what are the different register values in this example. So, we will be mainly concentrating at what are the register values for this instruction. So, what is the first command? First command is PC, memory address in, read, select 0, and this one. That means what I am trying to do over here, I am going to give the value of program counter to the memory address register, so that we can get the instruction out of it. Then what happens basically, after certain amount of halt etc., the second stage says that Z out to the program counter in and Y in. Y in is very special. So, in this case second instruction as we know. So, of course, this one corresponds to the incremental part, you are saying select 0, add and Z in. So, this thing means actually you have to add, select 0 means it is the constant, add means the ALU will add, and updated value of PC, that is PC plus constant. In this example 1 we are taking an example, will be in A, will be in the register Z. So, Z equal to Z plus 1, PC has been incremented. Second stage basically Z out PC in, the value of this updated program counter will be loaded into the PC, the PC is now updated. And as I told you, as a special case, in case of jump addresses, the updated value of PC is also given to Y. We have already seen Y, because you have to add the value of updated value of PC to the offset. So, you require 2 operands. So, one operand we are storing in the temporary register Y. Then what happens basically, then you have to wait for some amount of time. In fact, it is better that. So, in fact, what happens, this after certain amount of time, after all this halt etc., we are putting the halt instruction over here. After halting basically, when everything is saturated, the value of the instruction will be loaded over here. That is the branch instruction will come to the memory data register. That means after Y in, you should wait for WFMC. When it is done, it will come over here. Next what? Next, as I told you, it is very simple. The instruction from the memory data register will go to the instruction register. It is a very standard operation. Now what? Now 4. Now 4 here you are going to see. Now what you are going to see in 4, instruction of, that is your offset, select equal to 1 over here and add. That means offset plus offset is offset is already we know what is the value of offset, and select equal to 1 means you are going to take the value from Y. So, Y is having the value of program counter. Y is PC is now Y is actually having the value of program counter, and you are going to add, if you see offset field IR out. So, if you consider this as your ALU, already we have seen that the ALU is like this, it is coming from Y, because select is equal to 1, it is in add mode, value is going to Z register because of the Z in, and of course the other input is coming from the offset, because offset field of IR equal to out. So, this is your actually offset. So, we already have seen that Y is nothing but your PC if you are adding to offset. So, Z that is will be nothing but equal to 3200 over here, the jump address. You have already seen the calculation. Then we are going to see, so basically your Z is having the value of 3200 over here after doing the calculation in 4th stage. Now, importantly, whether this 5th stage, that is nothing but your Z will be loaded to the program counter or not, will depend on if the sign flag. So, if the sign flag is set as required over here, we are going to the 5th stage and the value of Z will be loaded to the PC. So, the PC will start executing instruction in 3200, or if it is a false, then basically the flag is not set as required. So, program counter value will not be 3200, it will be actually the address for the next macro instruction. The first macro instruction was branch on 0 3200. So, if it is not the case, it will actually come out of this whole micro instruction cycle and it will go out to the next macro instruction to be executed. So, basically, so we have taken another example in which case we have taken a branch on some sign, and we have seen that for these steps basically what are the values which are loaded into the different registers. You can just look at the PC and calculate for yourself, and you can get a very easy understanding. Now, we have seen about jump conditional and jump unconditional. Next is call and return. That is one very important thing. We have also seen that when we were discussing about some kind of a subroutine call, when we were looking at interrupt. So, every time we have seen that before we jump to a function or a interrupt subroutine service. So, what we do? We save the value of the program counter, we save the value of all the intermediate registers and all the stuff which we are doing in one function to a temporary scratch pad or temporary memory, go and service the interrupt, go or finish the procedure and again come back and again take up all the values of the temporary registers which we have saved and start executing. Basically, first very important is that we save the PC. We save the PC because when we will come back, we have to reload the value of the program counter and start executing from there. So, we have to always save the value of the PC in a stack, and along with the PC we save all the temporary registers. But to make it the discussion bit simpler, we will assume that only PC we are saving, all others are saved in a default manner, because that will actually make the discussion bit simpler. So, along with the same single bus architecture, but with only one addition, that is your stack pointer. If you look at it, I have put one stack pointer out over here. So, the stack pointer is very important, because in this case you have to save the value of PC, and where the value of PC will be saved is actually will be defined by a stack pointer. To make it simpler, as I told you, you are only showing for the PC, but along with the PC you have to also save other stuff like your temporary registers, accumulators, etc., which at the time being we are assuming that will be set as default. So, we will just go for function call and return. So, for example, the call is that we are calling function 1, and function 1 memory, let us say that 3200. That means what? We are calling, say call 3200. 3200 memory location actually have the first instruction of that function. So, our job is to jump to 3200, but before that, that means you have to load the value of program counter to 3200, but before that it is very important, maybe you are at program counter is maybe at 30. So, at 30 memory location 30, if you are calling it as memory location 30, memory location number 30 is having the function call that will jump to 3200. So, before executing this jump, that is before making the program counter 3200, we have to store the value 31, that is the next location, in a stack, because when I will be returning, I have to start executing from 31. That is the idea. So, we will see quickly how it works basically. So, the first three set will be very similar, fetching the instruction and putting it into the instruction register. Now, already we know that when we are executing up to micro instruction number 3, program counter has been incremented equal to program counter plus constant. So, this has to be stored in a stack. So, what we are doing? So, basically program counter, that is fourth stage, PC out, that is the updated value of program counter, we are putting it in the memory data register. That is simple, because we want whatever you want to write it to the memory, we have to put it into the memory data register. Next what? Next we are making the memory to a write mode, because the program counter has to be saved to a stack, which is the memory. Now, where I have to save it, that is very important. That is, this is your whole memory is there, maybe from here maybe the stack starts. So, now what happens? Here I have to store the value of program counter, that is the updated program counter plus constant. That is already updated in up to step number 3. Now, this is your memory data register, which we have already the value of PC has been stored over here, which has to be now dumped to the stack. So, the fourth stage, PC out, MDR in, basically the value of program counter is stored over MDR. Now, the MDR has to be written to the memory. So, we make the memory in a write mode, and what will be the memory address register value? It will be, memory address register value will be nothing but your stack pointer. So, stack pointer actually will grow upside or downside depending on the requirement. So, at present this is we are assuming that we are growing up. So, this was the first place where the current PC has to be stored. So, actually the stack pointer knows this position. So, the stack pointer value will be loaded to the memory address register. So, once it is done, of course, the value of program counter will be saved into the PC. So, basically this stage SP out, memory data register in, address register in means the program count stack pointer value will be saved to the memory address register, and there we will be saving the value of the program counter, as simple as that. Then next part it is, so we have saved the value of the program counter. Now, we have to dump the value of program counter, we have to dump the value of now 3200, because already we have saved the value of the program counter in the stack pointer. So, it is very simple, already we have seen. You have to wait for some amount of time till the program counter value has been saved, because before that if you update the program counter, there may be a race condition or there may be a problem. Now, you wait till your memory has been written So, you are safe. Now, you are taking the offset value of the register, select one, add and Z in. That is same stuff. We are actually making the offset value added to the program counter, which is nothing but it will give the value of the jump address, in this case is the call address. Then Z out you give to the PC in. So, Z actually in this case is equal to nothing but 3200. That is the same way offset you are calculating and adding with the present value of the program counter, you are putting in the PC and you are going to jump. Your job is solved. So, that is very similar to any other jump instruction. Only important part is this one. That is, you have to save the value of your program counter in the memory data register, and the stack pointer address has to be stored into the memory address register, so that the PC can be saved and then you write the memory. And then you wait till you do the jump. So, before we end, quickly have to look at what is the return, because once you have called, you should also return. Return is very important, as you have already seen. If your condition is false, you have to return. Function is ending, you have to return. So, return is as important as call. So, basically we will say return in this case, but return will not specify basically any address. But where we will go, basically let this be the stack. Stack will be pointing to some address, some content, maybe say 11, because we say jump from memory location 10. So, we will say return. So, return means you have to do nothing, no address calculation basically of that sort, just you have to look at the memory at the stack pointer, whatever value is there will have to be loaded to the PC, so that the PC can start executing from that location. So, again whenever there is the return instruction, the first thing will be extremely similar, that you have to dump the value of register in, R in will have the value of return, that value will, return instruction will come from there, all others will be similar. Then what? Now I have to return. So, what I will do? I have to actually load the value of the program counter, I have to know, update the value of program counter to the instruction where I have to start. I have stopped at one point in the main program, I have jumped. So, again I have to rego and start executing the main program. So, if you remember, we started in the example, we started from 11th location, up to 10th we had finished. The value 11 we have already stored in the stack pointer. So, in the stack. So, basically that is what the stack. So, some stack pointer was pointing at this point, and the value 11 we have stored over here. Now, we have to read back the value of 11 and put it into the PC. So, what we have to do? So, memory address register will have the value of PC now, because this stack pointer only knows where I have actually kept the last value of the PC. So, SP out memory address register in, as simple as that, because only the stack pointer knows where I have saved my last PC, and you have to make the memory in read mode, because you will be reading out it. You wait for certain amount of time till your job is done. So, whenever your reading is done, then basically your memory data register or the buffer register will actually have the value from here. That means, by 4th and 5th state what you are doing, you are actually writing the value of program count, you are actually taking the stack address to the memory address register. That is, you are going to take this address of this location to the memory address register and reading the value of 11, which is the program counter value from which will start executing after returning to the memory data register. After that, only one thing remains, you take this value from the memory buffer register or the memory data register and put it in program counter. Now, your program counter will have the value of 11 and you start executing from very left, as simple as that. So, call and return are very simple, just it is a jump instruction, but before making a jump, basically you have to store the value of the program counter in a stack pointer, and in return it is more simpler than that. Fetch the return instruction and go to the address of the memory where the stack pointer is pointing, load that value in the program counter, as simple as that, and your job is done. So, with this actually we have gone through all the different types of control signals that are required, and the sequence of micro instruction and the corresponding control signals when you are going for any kind of a jump instruction, both conditional and unconditional, and in the end we have elaborately discussed that how it is actually, it happens for a jump. It is actually a call and a return instruction. So, this special case also we have seen. Now, for the pedagogical completeness, let us see what are typical questions and how the objectives are satisfied. Like for example, in the first question we say, consider a CPU with a single bus, execute an instruction jump on 0 and jump on carry, briefly explain the control steps in each step and show how the control sequence executes. So, of course, this is satisfying the requirement of explaining the issues related to, it will be actually satisfying the next two objectives, use of flags because you are having conditions, and basically on a single bus architecture, use of flags while designing control transfer. So, basically this one will actually satisfy these instructions. And of course, this one is also very important because you have to explain the issues related to control transfer. So, if you are able to design instructions and the control instructions and the micro instructions, the control signals for jump on conditions like 0, carry, etc., then you are actually satisfying these objectives. Second question is that you are taking a single bus architecture, briefly explain the actions in terms of control signals that are involved in returning and calling a subroutine. So, in fact, if that is the case, then of course, you are satisfying the first and the last objective, because the last objective is design of instructions that is call and return for subroutines. So, with these questions, after doing this lecture, we expect that you will be able to solve this question and meet these objectives. So, with this we come to the end of this unit, and now till now what we have seen, basically you have seen what are the control sequence, what are the micro instructions, what are the control signals generated for all types of instructions like jump, load, store, different modes of addressing, and also in the end jump and control transfer instructions. Next is the very important question is that who will generate these signals and how. So, that is the heart of the whole control unit design. As we have already discussed in the first, while starting this module, that there are two ways of generating the control signals based on taking the inputs from the registers, flags and all other parts from the control bus is a hardware unit which will generate this. This can be either done by a hard-coded unit called the that is your hardware module to generate the control signals, or you can have some software approach like which is called microprogram control. One is the hardware control, one is the microprogram control. In the next few sequence of lectures in this unit module, we will be looking at how to generate these control signals both in a software manner, that is a microprogram control manner, or as a hard-coded hardware is a hardware unit to generate all these controls. In the next few sequence of lectures, we will see how these control signals are generated. Thank you.